Hello, welcome back to the IITians channel. And today we're revising week 4, and I hope you have watched the previous week's lectures. So today we're doing the concept of nested iterations and difference between normal and nested iteration. Also, we'll do the concept of binning, and we'll see how comparisons are made and how the concept of binning reduces the number of comparisons between two data. So let's get started. So we have nested iteration refers to a loop that is contained within another loop. So one loop contained within another loop. So let's say we have the while loop as in our pseudocode, which says some statement. And if this statement is true, there would be another loop, if loop, and which would have another statement. So we'll go to the if loop only if this statement is true, right? So that is how nested iteration works. One loop is inside the another loop. So we have a example here. You have to find the bigger of 3. It's not exactly like our pseudocode, but it's somewhat similar to Python. You'll understand it. So there's a command saying read A and read B and read C, and then they're checking if A is bigger than B, and if this condition is true, then we check if A is bigger than C, and if both these conditions are true, then we print A. But if this condition is false, the first statement will still holds true. Then we print C. So if both these conditions are true, then A is greater than both B and C. That is why we print A. And if the first condition is true, but the second is false, it means A is bigger than B and C is bigger than A. That is why we print C. So that is how we find the bigger of the three using nested iteration. And I have a flowchart for you so you can understand it better. So basically there's an outer loop condition. So let's say there's a while loop and it has some condition, and there's an inner loop. Let's say it's the if loop. It has some condition, and if the while loop statement is true and if the if loop statement is true as well, then this green box statement is carried out. But if this statement is false, this condition is false, and this condition is still true, then this goes here, and this red box statement is then carried out. But let's say if the outer loop condition becomes false, if this condition becomes false, then we do not look at the inner loop at all, because the point of having inner loop is checking the inner loop only when the condition on the outer loop is true. So then this goes directly to false and this goes to the statement. So that is how the nested loops work. Now, difference between normal and nested iterations. So in normal iteration, there's only a single loop repeating process. So if there's a while loop, every time the loop is correct, everything inside the loop will be carried out, right? But in nested iteration, there's a loop inside another. So we have to check multiple conditions and carry out multiple loops. So yeah, and the use when is it used? For normal iteration, we can use it while like counting or printing, so simple repetitive task. And with nested iteration, we can handle tables and grids and multi-dimensional data. So maybe we have a matrix or a table, and we have to do something with this particular cell. So first, in the first iteration, we check this row, and in the second iteration, we check this column, and that is how we obtain the value on this cell. I'm just giving a sample, like not an not an exact situation. So yeah, and then we have binning. Binning is a technique used in computational thinking to group or categorize data into discrete bins or intervals. It helps in organizing large data set, simplifying analysis, and improving computational efficiency. So, for example, you have a subject teacher, and the teacher receives like test papers from different sections. So for her, it would be easier to like carry out all the markings and everything if she separates the all the papers according to the sections. So section A, section B, section C, section D, and there's a pile for each section for her to make it easier for her to like find out the topper of each section and all that stuff. Or let's take an easier example. Let's say you have like Uno cards, right? And then I want you to find a plus 4 in it. So if you want to find a plus 4, you have to go through all the cards in the data set and you have to check if there's a plus 4. But you can distribute the Uno cards into 4 sections or 5 sections. That is red, green, blue, yellow, and then wild cards. So if the cards are distributed into all these sections and I want you to find out a plus 4, you would simply just go through the wild cards, not all the cards, right? So for you, the number of comparisons have been reduced. uh, it's easy for you to find the wild card because you have a separate pile or separate bin for the wild cards, okay? But if you want to go through all the cards, it will take you longer, right? So let's say after plus 4, I want you to find something similar to plus. I want you to find another plus 4. So I want to find another plus 4 and compare. So what a computer does is compare one card with another card to see if they're the same, right? So you already have a plus 4, and if the computer wants to find the plus 4 in the entire pile, then it will have to compare each and every card to the pile. But let's say there are total of only 4 wild cards, so there would be only 4 comparisons with this plus 4. So that is how we'll end up finding a plus 4. So in total, there would be a lot many comparisons. I don't know how many cards there are, but let's say there are 30 cards. So there would be 30 different comparisons in normal case. But in case we have a bin, if in case we have separate bins and we have a bin for wild cards, then we just need 4 comparison to actually find the wild card. So that is why we do binning, because the number of comparisons are reduced and the analysis of the data is simplified because we have categorized it. So here, if a bin has at most one card, then there is no need to iterate that bin. So at most one, as in either there's 0 cards or there's just one card. So if there's 0, of course, there's no iteration needed. And even if there's one card, there's no iteration needed because if there's two, if there's A and B, then you compare A with B. Or if there's A, B, C, you make 3 comparisons. But if there's only A, you do not actually compare A with itself. So there's only one comparison. So this is true. One iteration is sufficient to bin the cards. So for binning, there's going to be an iteration like while, let's say for the Uno cards, there are more cards, whatever. So if X is equals to red, then there's a bin for red. So we iterate it in red cards, red is equal to red plus 1. We add it to the red card, red plus X, sorry. And if the card is yellow, if X is equals to yellow, then there's gonna be yellow is equals to yellow plus 1 and so on. So if we go through this iteration, this is the only iteration needed to bin all the cards. So yeah, one iteration is sufficient. What is the advantage of binning? It reduces the number of comparisons. Of course it does. It avoids nested iteration. No, we can still use nested and binning together. They're like unrelated. So yeah, this is the only correct option. Comparing each element with all other elements. So for this, we use a formula. If there's n number of objects, if there's n for n objects, we use this formula, that is n into n minus 1 by 2. So this formula has to be memorized because it is very useful even in stats and maths. And I'll explain to you where this formula comes from so you remember it better. So let's say we have like 3 elements A, B, and C, and we have to compare each element with the other element in the group. So we can make a table for the comparisons A, B, C. So here we compare A with A, A with B, then A with C, then B with A, B with B, B with C with A, C with B, and C with C. So here we had three elements to start with, right? And what are the total number of comparisons? So total comparisons becomes n into n. That is three elements here into then three elements here is again compared with the three elements, same three elements, right? So n into n, that is 3 into 3. So we have 9. And as I told you, we don't compare the element with itself. So we'll reduce the number of self comparisons. That is, we'll cut out A, B, B, C, C, because it's the same elements, right? So how many elements got excluded? That is also n. So n was 3 here, 3 elements got excluded. So we subtract this n into n is basically n square. So we subtract n square minus n. So let's say if there was a D column as well, then this would have some values and then the last one would be D. So this would also be reduced. So for 4 elements, we subtract 4 elements again and it keeps on repeating. So that is why we subtract n. So we have 9 minus 3, that is 6 here. And you see here, AB, BA are the same. AC, CA are the same. BC, CB are the same. So each comparison here is doubled. So every time each comparison we make gets doubled because of this table. So we divide the total number of comparisons by 2. So we can divide n square minus n by 2. And we can write this as n into n minus 1. That is if we take the n common by 2. So n square minus n was 6. So we do 6 by 2, that is 3 comparisons. And this 3 makes sense because if we had A, B, and C, then we would compare A with B, then A with C, and then B and C together. So there's just 3 comparisons. So that is how we derive this formula here, and it can be used for any value of n. That is, no matter how many elements you have, you can use this formula. So yeah, this formula is shown here, n into n minus 1 into by 2. So let's say we had like 4 elements, right? A, B, C, and D. So we compare the corners first, B, A, C, B, D, C, D, and then we have to compare diagonals, that is B with C, and then A with D. So how many comparisons do we have? 1, 2, 3, 4, 5, and 6. Then we can verify this with the formula. So 6 comparisons. And what is n here? N is 4 elements. So 4 into 4 minus 1 by 2. That is 4 into 3 by 2, which is 12 by 2, which is 6. So we have verified it with the formula as well as with the diagram. And similarly, if we had like 5 elements, like in this diagram, so we have first compared the corners and then the diagonals, and then we have compared each corners with the element in the center, that is C. So we had initially 6 for 4 elements, and then each element is compared with the fifth element. So another 4 comparisons are added. So we have a total of 10 comparisons. And here as well, they have concluded it as 10. So yeah, and we can verify this formula using another method, that is NC2, using NC2. So if you have studied combinations, you would understand this. If not, you can write NC2 as n factorial by 2 factorial into n minus 2 factorial. That is n factorial by r factorial into n minus r factorial. So n factorial can be written as n into n minus 1 into n minus 2 factorial, and 2 factorial is basically 2 because it's 2 into 1. So 2 into n minus 2 factorial, and you can cancel these out. So then you're left with this formula, that is n into n minus 1 by 2. This is the same formula as here. And from first principle, this is the same thing that I explained here. So you can go through this and you'll understand it. And the number of comparisons can also be written as half into n into n minus 1. This is the same, they just took the 1 by 2, n by 2 as half. Calculation of reduction due to binning. So that is for the number of comparisons when there are no bins. So this is how we compare the elements. Now let's say we bin the elements. Let's say we have all the elements A, B, C, D, E, F, and then we bin them. We create 3 different bins A, B, C, D, E, F. So when we had A, B, C, D, E, F, the number of comparisons were n into n minus 1 by 2. That is, we have 6 elements here. 6 into n, 6 minus 1 is 5 into 5 by 2. That is 15. So 15 comparisons without binning. So this is without binning. And let's say k is the number of bins. So we have 3 bins here. So k is equals to 3 here. And if we have 3 bins, what are the number of elements in each bin? So here the number of elements are 2. A and B and C and D and E and F. But how do we write that? We can say n is the total number of elements, and if we divide it by the number of elements in one bin, we get the if we divide it by the number of bins, then we get the number of elements in one bin, which is 2. So 6 by 3, 6 elements by 3 is 2, and this is for, and if we want to find the number of comparisons inside one bin, so number of comparisons in one bin. So what would it be? So since we just have 2 elements here, we have 2 elements, so there would just be one comparison between the 2 elements. There's just one comparison here. Now we verify it with the formula. So in the first case, n was the total number of elements, but since the number of elements are reduced to n by k here, so we replace all the n in the first formula by n by k. So this will become n by k into n by k minus 1 whole divided by 2. Or you can also write this as 1 by 2 into 1 by 2, right? So this is for one bin. But if you want to find the total number of comparisons, we have to find the comparison in each and every bin. So in one bin, there's only one comparison between A and B. Then there's one comparison here between C and D. Then there's one comparison between E and F. So the total comparison is 3. So 3 comparisons that can be written as comparison in one bin, that is 1, into total number of bits, that is 3. So 1 into 3 is 1, right? So number of comparisons uh, in all the bins, that is after binning. We can write this as comparisons in one bin into number of bins, which is k. So what were the comparisons in one bin? This is n by k minus 1 into half. So n by k minus 1 into half, and into the number of bins k. So here this gets cancelled out. So we are left with n into n by k minus 1, and we can write this as n by 2, half as n by 2. So this is what we are left with, and we can verify it with the formula, the example above. So n by 2, n is the total number of elements, 6 by 2. N by k is 6 by 3, which we know is 2. So 2 minus 1. So we get this as 3. So we got this as 3 and this as 3 as well. So this thing is verified with both the formula and the theoretical explanation. Now we want to compare how the number of comparisons are reduced because of binning. So for comparison, or we can say reduction. So how many comparisons were reduced? So we divide the comparisons without the binning process by 2. This is comparison without the binning process by comparisons after the binning process was introduced. So after the binning process was introduced, these are the number of comparisons. We divide it with this n by k minus 1, and these get cancelled out. So we're left with n minus 1 by n by k minus 1. So in our example, n minus 1 is 6 minus 1 and n by k is 2, so 2 minus 1. So this is 5 by 1, which so it is reduced by a factor of 5. And you can also compare it with the example. Uh, as you can see, the number of comparison without binning was 15, and the number of comparison after binning is 3, and we get 15 by 3 as 5 as well. So the formula, the value we got with the formula and with the theoretical reasoning is the same. So this is how you do. You don't have to memorize anything here except this formula. This is the same formula as the one before, n into n minus 1 by 2. This is the same formula. And when you go for the number of comparisons after the binning process, the formula is the same, only that this n by k gets changed. This becomes n by k. K is the number of bins, and this is factor of reduction, which is given as n minus 1 into n by k minus 1. This page has the same thing as the ones I explained. If you go through it, you'll understand. Basically, just remember this, and you can remember this formula as well using the first one. And this is simply dividing the first and the second, so you get this value. Like I showed you here, we divide the ones without binning. This is without binning and after binning. So we get this value. This is the same as this one. So yeah, I hope this is clear. In summary, the number of comparison between all pairs of items grows quadratically. So for example, if there's only one item, there's no comparison. If there's two items, if n is equals to 2, there's one comparison. If n is equals to 3, then there's 3, sorry. Yeah, if n is equals to 3, then there's 3 comparison. If n is equals to 4, then there's going to be 6 comparison. We saw it here. And if n is equals to 5, there's 10 comparisons. If n is equals to 6, we have 15 comparison. So you see how the number of comparison is growing. So it's quite fast. And this is the formula for the comparisons. And sometimes it's possible to find a heuristic that allows us to put the items into bins and compare only the items within bins. So this is binning. If there are n items put into k bins, each of them are equal size, and the number of comparisons would be this, and the factor of reduction is this. So you just have to memorize this formula. We have n cards in a pile. We compare each card with every other card in the pile exactly once. What is the total number of comparisons made? So there's no binning or anything here, so it's a straightforward question. So you'll put the formula itself. Consider the following 7 elements. If we connect each element with every other element, so that by a line that is comparing each element with every other, it's the same thing. What is the total number of lines that we would have to draw? So you can just use the formula n into n minus 1 by 2 here. It's the same. Like whether we compare two items or whether we draw a line between them, it means the same thing. So we have 7 items here, 7 elements. So n is 7. 7 minus 1 is 6 by 2. So we have 7 into 3, which is 21. As mentioned in the lecture, assume that the computer can do 10 to the power 8 comparisons in 1 second. How many seconds will it take for the computer to pairwise comparison of 1 million elements? So we want pairwise comparisons of 1 million elements. 1 million is basically 10 to the power 6. So we use the formula, same formula, n into n minus 1 by 2. N is 10 to the power 6 and n minus 1, that is 1 million minus 1. So it would be this number by 2, right? So this is a pretty large value and we can cancel this off. So we will get 500,000 into 999,999. We'll get this value as the total number of comparisons. And then it says the computer can do these many comparisons in a second and you have to find the number of seconds. So we can divide for the total, to find the number of seconds, we divide the speed of the computer by this by the total number of comparison, which is 10 to the power 8. So we can cancel off 1 2 3 4 5 6 sorry 5 zeros here. So this is 10 to the power 3 then, and then this 99999 is this, we can basically round it off to 1 million, that is 1,000,000,000 because it's a pretty large value and adding 1 doesn't make a difference. So we can cancel this off. So the total is 5 into 1000. So we have 5000 here. So nearly 5000 seconds. It will be slightly greater than 5000 seconds, but we have to approximate, so it's fine. Assume that we have 20 objects that need to be compared. How many pairwise comparison do we need to make if each object is compared with every object exactly once? So no binning or anything, simple formula. So that is 20 into 20 minus 1 by 2, which is 20 into 19 by 2, that is 190. Assume that we can distribute 20 objects into bins of equal size. If we go 4 bins, that is 4 is k, how many comparisons would we have to make overall? So we use the formula that after binning, that we used after binning. So that is n into n by k minus 1, and we can write this as n by 2. So n by 2 is 20 by 2, 20 by 4 minus 1. So this would be 40. Next, we distribute 20 objects into bins of equal size. How many bins should we choose to make the least number of comparisons? So how do we make the least number of comparison in one particular bin? That is when we have 2 objects. That is when we have just one comparison in one particular bin. That is just 2 objects in one bin. So we just want 2 objects. So in that case, if we have 20 objects, we can divide 20 by 2, we can get 10 bins. Based on question 1 and 3, what factor does the binning reduce the number of comparison? So we can simply divide the number of comparison without the binning and after the binning. So after the binning, there's 10 bins and there's one comparison in each bin. So 190 by 10 is 19. Next, we want to find the number of pairs of students who satisfy both the conditions given below. Both students in the pair have same total marks and both students do not belong to the same gender. So same marks but different gender. We divide the students into 2 bins, one which contain boys and the other which contain girls, and perform pairwise comparisons within the bin. Will this approach give us the correct answer? So no, because we are comparing within the bin. That is, we are comparing boys with boys and girls with girls. There's no comparison between boys and girls. But in the question they ask, they do not belong to the same gender. So this will not give us our answer. So we have data about the birth dates of 100 people in a room. We wish to find the number of pairs of people who were born in the same year. Which of the following is the most ideal binning strategy? Use 12 bins, one for each month. So this would not work because we want people of the same year, not the same month. Use two bins, one for people born before 2000 and one for people born after 2000. So this can work, but let's see whether the third option is correct. Use 12 bins, one for each decade starting from 1900. So we have more number of bins here. Both of these both of these methods are dividing the number of people based on the birth year, but we have greater number of bins here. So this third option becomes more strategic. This becomes more better because the more bins we have, the lesser the number of comparisons. So the number of comparison is the least in this case. So it would be easiest to find the number of people having the same year in this case. That is why this is the most strategic option. Now we wish to count the number of students in the bin 201 to 225. So this is for marks bin. So we want to count the students in this bin and store the result in variable a. Which of the following if condition check if card X falls in this range? Assume that A has already been initialized to 0. So A is already 0. So in the first option, we are checking if A, if X total is lying in between these two endpoints. So the endpoints are marked correctly. And we're checking if A is equals to 1. So this is wrong because it's not incrementing A. This is checking if A is equals to 1. So we don't want to check if A is 1. We want to increment A, right? So this is wrong. And in the second option, if X total is between 201 and 225, this is the endpoints are correct and increment A is incremented correctly. So this is for incrementing A and that is what we want. So this option is correct. And in the third option, they have used the boundaries as 201 and 226, but this is also correct because they have used greater than here, not greater than equal to. So it's gonna count from greater than 200. So 201, 202, 203 up to 225, excluding 200 and 226. So that is why these two endpoints also become correct, and then A is also incremented correctly. So this option is correct. And in the fourth option, they have separately used if X total is greater than 201, then we enter this loop if X total is less than 225. So this is a nested loop. We are entering the second loop if the first condition is satisfied. So if X is greater than 201, so let's say there's two boundaries here, 201 and 225. So the first condition is checking if X is greater than 201. So if X is greater than this, so the point before 201 is already excluded. So the point on this side is already excluded. Then in the second statement is checking if X is less than 225. So if X is less than 225, so in that case, this endpoint is excluded. So everything that's greater than 225 is excluded. So then we get this boundary, that is 201 and 225. So this is also correct because the endpoints are correct. So and then A is incremented correctly. So this option is also right. Let X and Y be the cards of two students. are the following code blocks equivalent? So we have to check if code block 1 is same as code block 2. So in the first one, if date of birth of X is equal to date of birth of Y, return true, else return false. And in the second, if date of birth of X is not equal to date of birth of Y, then return false, else return true. So in both the cases, we get the value as true if they have same date of birth, and we get the value as false if they have different or non-equal date of birth. So both these code do perform the same action, so they are both equivalent. So this is a yes. So that was the last question, and we're done with week 4, and you will be probably giving your qualifiers or quiz 1 soon. So I hope you understood all the topics till now, and I hope you're practicing the questions. And do let me know if there's any feedback or if you like my lectures. Thank you for watching, and all the best for your qualifiers.